In this video, we are going to discuss basic proportionality theorem, which is invented by a Greek mathematician Thales. So nowadays, it is also called as Thales theorem. Now, what does this theorem states? If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then other two sides are divided in the same ratio. It means that if we have given a triangle and if we draw a line parallel to any one side of the triangle, then that line divides other two sides in the equal ratio. Now, to understand this theorem in more details and to prove this, let us draw figure according to the given statement. Let us draw figure. We have given a triangle. Let us say it is triangle ABC, and we are supposed to draw a line parallel to any one side of the triangle. So let us draw a line parallel to side BC. Say that this line intersects side AB in point D and it intersects in point E to side AC. Now let us write the given things. Given we are going to write from the figure. So in figure we can see that ABC is a triangle in which line DE is dividing sides AB and AC in two distinct points D and E such that this line DE is parallel to BC. Right? Now we are going to prove that this line DE divides side AB as well as side AC in the same ratio. Means AD upon DB is equal to AE upon EC. After this, to prove the theorem, we require to do a construction. Now, what is the construction? First of all, we are going to join CD and BE. After that, we are going to use the concept of area of a triangle, which equals to half into base into height. So, for that case, we are going to construct perpendiculars from points D and E on sides AC and AB respectively. So our construction is draw DX perpendicular to AC and EY perpendicular to AB. So first of all we'll construct perpendicular from D and then from E. Now we'll say point X, DX is perpendicular to AC and another point we'll name as Y, EY is perpendicular to AB. So this is the figure. Now we will see proof of this theorem. To prove this theorem, first of all let us consider the figure which we have already drawn. Now we know the formula of area of a triangle which equals to half into base into height. Right? Now we are going to consider the ratio of area of triangle ADE and triangle BDE, because in the proof we are going to show that AD upon DB is equal to AE upon EC. So we are considering a ratio of areas of two triangles in which AD and DB are the bases. So AD is the base of triangle ADE and BD is the base of the triangle BDE. So we have considered their ratio of their areas. Now this we can write area of triangle ADE is nothing but half multiplied by base is AD and height is EY. For triangle BDE, BDE is an obtuse angled triangle. So its height is lying outside the triangle because we have considered BD as the base. So its base is BD or DB and height is EY again. So by doing the cancellations, half will get cancelled from numerator and denominator as well as EY will get cancelled. So that is equal to AD upon DB. So let us consider this as equation number 1. Similarly, on the right side, we want AE upon EC. So let us consider the triangles in which AE and EC are the bases. So ADE again is the triangle having base AE, and triangle CED is the triangle in which EC is the base. So let us consider the ratio of the area of triangle ADE upon area of triangle CDE. So area of triangle ADE, here we can write half multiplied by base we are taking as AE, means height will be dx. And for triangle CDE, base we have taken CE as it is obtuse angle triangle, and we have taken CE as base, its height will be dx only. So that is half multiplied by EC into dx. So half and dx will get cancelled from numerator and denominator. We will get this is equal to AE upon EC. Let us call this as equation number 2. Now, if you observe equations 1 and 2, we can see that the numerators of both the equations are equal, where we have considered ratio of the areas. It is the same triangle ADE, but the denominators are different. Okay, in the first equation on the left side in the denominator we have triangle BDE, while in the second equation we have triangle CDE. Now if we observe triangle BDE and triangle CDE, we can see that both the triangles are lying on the same base DE and between the parallel lines DE and BC. We know that if two triangles are lying on the same base and between the same parallel lines, then their areas are equal. So here we can say that area of triangle BDE is equal to area of triangle CDE. Let us consider this as equation number 3. Now, from equations 1, 2 and 3, we can say that numerators on the left handed side are already equal, and from equation 3, we have shown that denominators are also equal. Means areas of the triangles in the denominator are also equal. So we can say that area of triangle ADE upon area of triangle BDE is equal to area of triangle ADE upon area of triangle CDE. Right? Now from equations 1 and 2, let us replace values of these fractions. So area of triangle ADE upon area of triangle BDE is nothing but area upon DB from equation 1, and area of triangle ADE upon area of triangle CDE is nothing but AE upon EC from equation number 2. So this we can write from equation numbers 1 and 2. This is the proof of basic proportionality theorem or Thales theorem. Now let us see the converse of BPT. To understand converse of this basic proportionality theorem, let us once again revise what exactly is BPT. In BPT, we have seen that if we draw a line parallel to any one side of a triangle, then that line divides other two sides in the same ratio. Right? So converse of this statement will be, if in a triangle a line divides any two sides in the equal ratio, then that line must be parallel to the third side. That is nothing but converse of BPT. Let us see the statement of this. So if we have a line which divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Let us draw the figure to understand this theorem properly. So let us consider a triangle ABC in which suppose DE is the line which is dividing sides AB and AC in the same ratio, that is AD upon DB is equal to AE upon EC. Then we can say that DE must be parallel to BC. So let us write this. In triangle ABC, line DE intersects sides AB and AC in points D and E such that AD upon DB is equal to AE upon EC. Means this line DE is dividing sides AB and AC in the same ratio. That is AD upon DB is equal to AE upon EC. So we can say that this line DE is parallel to the remaining side, that is BC. So we can say that DE is parallel to BC by converse of BPT. Now let us see one example based on BPT. If a line intersects sides AB and AC of a triangle ABC at D and E respectively and is parallel to BC, then prove that AD upon AB is equal to AE upon AC. This question can be considered as a corollary of BPT also. So here let us draw the figure. First of all, let us consider the given triangle ABC. Here a line divides sides AB and AC in points D and E, and that line is parallel to BC. So let us start writing the given things. In triangle ABC, line DE intersects sides AB and AC in points D and E such that DE is parallel to BC. So we know that in a triangle, if a line is parallel to the one side of the triangle, then it divides the remaining two sides in the same ratio by BPT. So here we can write AD upon DB is equal to AE upon EC by BPT. Now, in order to prove the given statement, there is a particular method. First of all, we are going to take a reciprocal on both the sides. By taking reciprocal, we can write DB upon AD is equal to EC upon AE by taking reciprocal on both the sides. Now we will add 1 on both the sides. Adding 1 on both the sides, the equality will hold true, because we know when equals are added to equals, wholes are equals. Okay. Now by doing the cross multiplication, we'll get DB plus AD divided by AD is equal to EC plus AE divided by AE. Adding DB and AD, we will get AB, and adding EC and AE, we will get AC. So that is nothing but AB upon AD is equal to AC upon AE. Now once again let us take reciprocals on both the sides. So we will get AD upon AB is equal to AE upon AC. This is the proof of the given question. So remember the steps what we have done. First of all, we have used BPT. We have taken reciprocals on both the sides. We have added 1, and once again we have taken reciprocals on both the sides. So this is the way of proving this corollary, or you can consider this as a question also.